Indistinguishability of identical particles is wrong. We think that we can distinguish two nitrogen molecules because they exist at different positions. But modern physics say two nitrogen molecules are indistinguishable. And two diamonds which have carbon atoms of the same number and same shape are indistinguishable. And two electrons are indistinguishable, even if they are one light year away. And two photons, which are in the different black bodies and have different energy, are indistinguishable. Can you believe it? Why did modern physics start to think that identical particles are indistinguishable? Because modern physics think that entropy must be additive and extensive. To establish the additivity, modern physics start to think that identical particles are indistinguishable. But the additivity is wrong. According to thermophysics, changing entropy is extensive. Then changing entropy must be additive. But entropy doesn't have to be additive. Now, we will show that entropy doesn't have to be additive, and changing entropy is additive by using Boltzmann's entropy definition. We will show that entropy doesn't have to be additive by using high school mathematics. Number of states in physics is equal to number of cases in mathematics. Let's think about the number of cases which we put distinguishable n-stones on capital N squares. The number of cases is like this. And the entropy S sub T equals about K log capital N to N. The number of cases omega sub A, which we put N sub A stones on the part A, is like this. And the number of cases omega sub B, which we put N sub B stones on the part B, is like this. Many texts say omega sub T equals omega sub A, omega sub B. But it is a basic error. The number of cases which we divide n stones to n sub A and n sub B is the number of combination of n elements taken n sub A at a time. Therefore, omega sub T is like this. We can gain correct total entropy from this relation, and we can show entropy is not additive. In the formula, we can indicate the total entropy K log capital N to the N. It means that Even if we divide the ideal gas by the partition, total entropy doesn't change. In statistical physics, omega is the number of microstates which are same macroscopically. Let's divide an ideal gas to part A and part B by a partition. How many microstates are same as states 2? Macroscopically, can we make? The answer is like this. Then, in statistical physics, entropy is not additive. Next, we will show that changing entropy is additive. Let's think about the number of cases which we put n stones on the n squares. The number of cases is equal to n factorial. Then the entropy is like this. Now we call this state minimum state. If the number of squares increase from n to capital N, how much the entropy change? How much the entropy of part A and part B change? This is the changing entropy of part A. And this is the changing entropy of part B. And this is the changing entropy of total. By using this relation, we can show that changing entropy is additive. Misunderstanding by modern physics. To establish this equation, modern physics start to say that each number of cases like this, and identical particles are indistinguishable. There is no reason which we must think that entropy is additive. Then there is no reason which we must think that identical particles are indistinguishable. Indistinguishable? No.